After having learned about the Wells-Riley model regarding the physics of COVID transmission, we are here to explain the aerosol estimator, which uses the Wells-Riley model to calculate the infection rate of COVID-19 in a given scenario. The Wells-Riley model utilizes the equation 1 minus e to the negative I lowercase p lowercase q t over uppercase Q, where uppercase p is the probability of infection, I is the amount of infectious people in the space, lowercase p is the average breathing rate of everyone, lowercase q is the quanta generation rate, t is the exposure time, and uppercase Q is the airflow rate of the HVAC system.
When creating our scenarios, we had to consider many different parameters. We chose an indoor place that we were interested in and researched information regarding those places. These parameters were the dictators of how the results came out. Once we chose a scenario and duration of the event, we researched environmental parameters such as the size, pressure, temperature, and humidity of the room. One of the most important parameters we researched was the ventilation with outside air, or the air change rate. The air change rate is the measure of air removed and replaced from a space within 1 hour divided by the volume of its space. This value can be changed through opening or closing windows or increasing ventilation systems. We then researched the parameters related to the people and activity in the room. These included number of people present, number of infected people, fraction of people immune, susceptible people, mask efficiency, fraction of people with masks, and quanta emission rate. The mask efficiency rate is how well the mask prevents someone from inhaling COVID aerosols. The quanta emission rate is a unit of aerosol pathogens whose inhalation leads to infections. These values are defined through probabilities. To help understand this, here is a table that shows different quanta emission rates based off the activity one person is doing. These parameters that I just explained are essential to understanding how the estimator works. So, how does the estimator work? The estimator we used in this lab is intended to estimate the spread of COVID-19 by aerosol transmission only. As we have learned, it is based off of the Wells-Riley model, and in order to use it, we researched the parameters I described above and inserted these values into a spreadsheet. The estimator then calculated the values and presented them to us in a data table. As you can see, there are different colors. These colors are very important for understanding how the estimator works. The orange boxes are the values that we research for our own individual scenarios. The yellow boxes are common values given by the estimator, and the blue boxes are our results.
When looking at the results of all the different scenarios our class chose and calculated, we can notice a couple of parameters that play a large role in protecting us from the virus and also certain circumstances that increase the probability as well. The most common scenario that was researched in our class was the circumstance of people in a car, either driving in carpool to school or a long road trip. For the results of this scenario, there is a considerably low probability of contracting the virus. One important thing to note is that when people who were in the car were not wearing masks, the probability of infection increased the absolute percentage of infection by at least 4%. Another parameter that affected this percentage was the duration of the event, such as the 10-hour road trip. Although the passengers were wearing masks, the absolute value increased again by at least 4% from a shorter car ride that was around 30 minutes long. Observing these changes in the same scenario, such as wearing a mask and the duration of the car ride, can help us recognize the importance of the different parameters. One conclusion we can also make from the results of our class is the amount of exercise during the duration of the scenario. For example, a yoga studio can significantly increase the probability of infection. Excessive exercise while wearing no masks in a room set to 105 degrees are perfect parameters to contract COVID-19. At the percentage of 89%, this is the highest probability of infection for a scenario. Finally, another important scenario to note was the probability of infection during a 1-hour-long class. The probability was significantly low at an absolute percentage of 0.021%. This result is important to us students because it is comforting to know that we are safe at school if all the rules are being followed.
We get our results in two main categories, conditional and absolute. Here we have the conditional results. These rely on the fact that the amount of people that you input as the amount of people that are infected are the actual amount of infected people in the situation, and therefore assumes that you know the actual amount of infected people, which is rare in many real-life scenarios. These results tend to be higher than the absolute results and tell us, given the scenario's circumstances, the chance of a person getting infected, being hospitalized, or dying. For more context to the significance of these numbers, we have the ratio of the risk to dying in a car-related accident. Then we have the amount of people in the event who would be getting infected, hospitalized, or dying. Then we have the absolute results, which instead of using your inputted amount of infected people, takes an estimate on the amount of infected people based on the infection rate in your community. These results tend to be lower than the conditional results, since instead of having a confirmed person is infectious, there's only a chance that someone is infectious. Again, we have the same chances with the conditional results for both the chance of an individual or the metric of the whole population participating in an event.
The estimator we use is not perfect, and there needs to be assumptions made. There are two assumptions within the estimator that I will talk about. The first assumption is well-mixed air. This is assuming that the COVID particles are dispersed evenly throughout the room, which is represented by the top of this image. The particles are not affected by ventilation, which is not correct. This is mostly not accurate because the majority of the time you're in a room, the COVID particles will be concentrated in specific areas depending on where the person with COVID is and how the air is being circulated. As you can see in the image, the particles in the air are manipulated and redirected because of the airflow within the room. The second assumption is well-mixed population, which is an assumption that everyone in the room is being infected an even amount. This is not accurate because the person with COVID could be only talking to one or two people, who are going to be much more likely to become infected than the other people in the room. Something to consider when reviewing the results is the precautionary principle, which is a way to approach an innovation that has the potential of causing harm when there is not enough scientific knowledge around the subject. The principle pushes a lot of review and caution before proceeding. When we look at our results, we have to use the precautionary principle because of the amount of uncertainties within the results and how those uncertainties could affect the chances of getting COVID.